Okay, welcome back to this course on DSP. In the last class, we have discussed discrete Fourier transform, and if you remember, we have defined DFT using equation this is the equation of DFT. Okay, and this Wn, which is called as phase factor or Tweedale factor, it is given by raised power minus j 2 pi by n. Okay, and corresponding to this, we have another equation for IDFT. Okay. Now in this class we will discuss the first Fourier transform, which is called as Fft algorithm. Fast Fourier transform is basically an algorithm which is used to compute DFT in a very efficient manner. Okay, means the computational complexity of this transform is reduced when you apply Fft. Okay, it is not a transform basically, it is a method to calculate DFT very efficiently. That we will see how it is efficient as compared to the direct computation of DFT. And if you see the computational complexity of DFT using the direct computation, means using the equation of DFT itself. So you will see that how many to compute endpoint DFT of a sequence, how many multiplications and additions are required. Okay, if you compute the endpoint DFT from this equation, it means your k will vary from 0 to n minus 1. You have to compute endpoints, and when you compute each point, how many multiplications you require. So for each value of k, your n will vary from 0 to n minus 1. It means there are n complex multiplications. Okay, like suppose if I compute the 4-point DFT of a sequence, I take xk is equal to n from 0 to 3 in that case. Okay, when my n is 4, and x of n wn to the power k. Okay, so it will be x0 plus x1 wn to the power 1 is 1 k, then plus x2 wn to the power 2k, and finally x3 wn to the power 3k. Okay, this is what is xk. And how many samples of x I have to find? I have to find x0, x1, then x2 and x3, right? And in order to find x0 only, I have to put simply now in this equation k is equal to 0. I will get x0, then x1, then x2, x3 and x so on. So for finding a single sample of DFT, how many multiplications are required? This is 1, this is 2, this is 3, this is 4. Okay, and of course in this case it is multiplied with 1 when n is equal to 0. And if you see when how many additions will be required, additions is 1 less than n, so you have to use only 3 adders. and 4 multipliers. Okay, so it means to compute a single point of DFT, when you use endpoint, you need n multiplications and n minus 1 additions for single point. So how many points are there total? N points. Okay, so total multiplication will be n into n. It will become n square, and total number of additions is n into n minus 1. Okay, these are complex multiplications and additions, of course. Okay, so n is the total number of output samples, and this n in this case, capital N, is the number of multiplications you need to compute single sample of DFT. So total number of multiplications is n square. Similarly, to compute one sample of DFT, you need n minus 1 additions, and since there are total n samples, so total number of additions will be n into n minus 1. Okay. Now we will see that how you can reduce this complexity of computation of DFT using fast Fourier transform. Okay. So in the fast Fourier transform, there are different algorithms. We will first develop a general approach, which is called as divide and rule approach. Of first Fourier transform algorithm. Okay, so as the name itself suggests, what we do in the divide and rule approach, we break a higher DFT into smaller DFTs. Okay, and then by combining those smaller DFTs, we calculate a higher point DFT. Like suppose if you want to compute 16 point DFT, so you may decompose 16 into 2 DFTs to 8 point DFTs. Okay, so first we compute 8 point DFTs and then we combine them to calculate a 16 point DFT, right? So there are special algorithms for this that we will discuss, which is called as Radix 2 Fft algorithms, which are used when the n is in the powers of 2, that is when n is 4, 8, 16, 32, 64. The algorithms in that case even becomes more efficient. But using this approach, divide and rule approach, you can compute any DFT. Like suppose if you want to compute the 15 point DFT. Okay, so for computing the 15 point DFT, we will decompose 15 into 2 factors, prime factors 3 and 5, and then we use these small DFTs, 3 point DFT and 5 point DFTs, and then we combine them to get a 15 point DFT. This is what basically we do in the fast Fourier transform. And how we do this, that we will discuss. So first thing is that if you want to compute the endpoint DFT of a sequence, we first decompose L into two numbers, L and M. Okay, like if n is 15, so 15 can be decomposed as 3 into 5. Okay, or if it is suppose 12, you can decompose it as 3 into 4, or you can also decompose it as 2 into 6. Okay, it is your choice. So first point is that this n will be decomposed into the product of two numbers, L and M. Okay, and then what we do, we store the data, the input data, in a two-dimensional array, a matrix of L cross M. Okay, means we have first xn, which is an n-point sequence, so we can store this data in a one-dimensional array of 1 cross n matrix, So you have x0, x1, x2, x3, x4 and so on, and last is x of n minus 1. This is the input sequence for which you are going to compute the DFT. Okay. Now since we have divided n into two factors L and M, so you can create a matrix, a two-dimensional matrix of order L cross M that is having L rows and n columns. Okay. Now in this case, when it is a single one-dimensional array, your small n is the index. So it is x0 here, then x1 here, and x2. Now when you have two-dimensional matrix, you must have two variables for indexing. Okay. So you have L rows and M columns. So the first element of this matrix will be denoted x 0 0. Then this will be x 0 1, x 0 2, and so on. Similarly, in this case, it will become now x1 0, x1 1, 1 2, and so on. It will become x2 0, x of 2 1, x of 2 2. So you need two variables for indexing, one for row and one for column. So I use here index is small n and small m. Okay. So small l is for rows, small m is for column. So if you see in the first row, your L remains fixed, it is 0. Okay, and the column variable m will go from 0 to ahead. Okay, in fact it will go from 0 to minus 1 because you have m columns. If you go along this rows, in this case the column variable 0 m, it is fixed. So the indexing of the row is changing 0 1 2, last will be L minus 1 here. Okay, so this is the first step. So you have to divide this n into two prime factors L and M, and then you have to create a two-dimensional array of L cross M. Now when you create this two-dimensional array, then you have to store this information, the input sequence, into this array. It means the one-dimensional data, it is mapped into a two-dimensional data. Okay, and how you fill this matrix of L cross M, there are two ways. Either you can fill the data row wise, or you can fill the data column wise. It means you fill the first column, then second column, and so on. Suppose I take a very simple example. If you have n is equal to, maybe if n is 6, okay, and I decompose it as 2 into 3, L and M. So 2 is L, 3 is my M. So you have a two-dimensional matrix having 2 rows and 3 columns, 2 by 3. So this is x00, x01, x02, and x10, 11, 12. Okay. So n is equal to 6. You have 6 elements in the input vector. So they should be now mapped into this two-dimensional vector. So either you can fill the data using the column-wise mapping or using row-wise mapping. If I fill the data using column-wise, it means I must fill first column, then next column, then second column. So it means x0 will be here, x1 will be here, then x2, x3, x4, x5. Okay, and the second option is that you store the data using the row wise mapping. The matrix order is same but you first fill the first row, then you fill the next row. It means you place data like this: x0 here, then x1, then x2, then x3, x4 and x5. Okay, so in both the cases, whether you use a row wise mapping or you use a column wise mapping, so there is a one-to-one relation between this indexing small n and this variables l and m. Okay, so n and this l and m, they have a mapping. Okay, so in column wise mapping this relation will be different. In row wise mapping you will have different relation. Okay, now if you use a row wise mapping, this one, so what will be the relation between n and this lm? It will be simply, for this case, it will be n is equal to ml plus m. Okay, and you can verify it when your l and m, they are 0 zeros. For this case, this point is x of 0 comma 0. What will be n? N is 0. It means x of 0 0 at this point, the data that is filled is x0. And when you're now for this point, this is my x01. Similarly, this is x02. So if you compute from this relation, when l is 0, m is 1, l is 0, m is 1, you will get n is equal to 1. It means for x01, you are getting x1. Similarly, for x02, you are getting x2. Okay, it means this is filled with x0, this point is filled with x1, this point is filled with x2. Similarly, if you compute here, it will be filled with x3. This point is basically x of 1 comma 0, and this will be having a data x3 from the original sequence. Okay, so this point which is x of 1 comma 1, it will have x of 4, and this point which is 1 comma 2, it will contain x of 5. So it is a row wise mapping. Okay, and similarly, if you have a column wise mapping like this, you fill the first column, then second column, then third column. In that case, the relation between n and this lm will be n is equal to l plus m into capital L. Okay, so if you compute from this relation, you will first element will be filled here, then second element will go here, then third element will go here, fourth will go here, fifth here, and sixth here, like this. Okay, so this is the first step, that you have to divide n into two factors l and m, and you have to store this one-dimensional data into a two-dimensional matrix of l cross m, and you have option whether you can store the data in the column wise format or in the row wise format. Now similarly, when you compute the DFT of this sequence, now endpoint DFT, that is xk. Okay, so that data can also be stored in the same matrix of l cross m, isn't it? You have an input sequence x of n, which is having a length of n points. We have decomposed n into two factors element, and then we have stored this one-dimensional data in a two-dimensional array of order l cross m. Okay, similarly, when you compute its DFT xk, it is also of n point, so it means the output can also be stored in a matrix of l cross m, either using the row wise mapping or using the column wise mapping again. So here we use a different variable. Suppose I use here indexing PQ. Here we have used LM. Okay. So the first point it was x of 0, 0. This is x of 0, 1, 0, 2, 0, 3 and so on. So L and M indexing I am using for the input sequence. P and Q, these variables I am using for the output, that is DFT. Okay. Now you have different options here, that which type of mapping you want to use for the input data and for the output data. Okay. So in the input data we have seen that your mapping is n is equal to ml plus m for row wise, and it is equal to L plus M into capital Y L. You store the data column wise. Similarly for the output you have the same relation, but now this is the relation between K and PQ. So K will be equal to MP plus Q in one case, that is for row wise, and K will be equal to Q capital L plus small p if you use a column wise mapping for the output. Okay, so you have to decide which type of mapping you want to use for input and output. Okay, so let us suppose that we use column wise mapping for the input and row wise mapping for the output. Okay, it means you store the input data in the column wise format. You fill the first column, then you fill the second column, then third column and so on. And when you store the DFT of this, we use a row wise mapping. It means you fill the first row, then second row, then third row. It means you will get first element here x0, then x1 here, then x2 here, x3 here and so on. Okay, you fill the first row, then you fill the next row and so on. Here you fill the first column, that is x0, then x1, then x2 and so on. It means I have chosen this mapping for the input and this mapping for the output. Okay, now once you have decided this mapping, the DFT of the sequence xk, which was x of n wn to the power kn, n from 0 to n minus 1, this is the original DFT. Now since we have stored this DFT in a two-dimensional matrix, so this single summation can be converted into a double summation, one summation for your column and one for row. Okay, in place of x m you will get x of lm and wn to the power k and n. Now k is for output, n is indexing for input, and we have taken for input we have taken column wise mapping. It means your n was ml plus l, and for output we have taken row wise mapping where k was mp plus q. Okay, this is input, this is for output, which is a row wise mapping. So this is wn to the power k. In place of k you can write now mp plus small q multiplied with n, which is your ml. This is small m, sorry, small m into l plus l. So if you expand this equation, you basically get the same as from this equation. Okay, and you can simply verify it. Now when this was the case, your data was stored in a single array, one-dimensional array. Now when you have divided this n as a factor of two numbers l and m, you have stored the data in a two-dimensional array and we are using the column wise mapping. Okay, L cross M. So you are using x0, you are filling here, then x1 you are filling here, then x2 you are filling here, and so on. Last element will be x of L minus 1. Okay, then XL will come here. This will be the x of L plus 1 and so on. Okay, so it means this one-dimensional array is mapped into a two-dimensional array, and this single summation is now converted into a double summation. So you have one summation for row, one summation for your column. So when M is 0, I will go from 0 to L minus 1. So M is 0, it means you are fixing the first column basically. When M is 1, in this series, again L will vary from 0 to L minus 1. So you are basically taking the second column, and third column, and so on. Okay. So if you compare these two equations, you will get the same output. Okay. Let us try for one sample. Suppose if you find xk from this equation, suppose for k is equal to 0, and now in this case it will become x of pk. It will also become a two-dimensional matrix. Output is also two-dimensional array. Okay. From equation number 1, if I compute x0, k is equal to 0, and will vary from 0 to n minus 1, I will get x0 plus x1 w to the power k is 0, n is 1, so it is everywhere 0. It means it is simply this factor will always be set to 1 because k is 0, so w to the power 0 is always 1. So the first element is simply x0 plus x1 plus x2 plus x3 up to x of n minus 1. Sum of all the elements. That is your first sample x0. Now if you compare from this point, the first element of this, that is when x 0 0 pq, p is 0, q is 0. Okay, and if you solve this equation, so for m is equal to 0, you will get L terms. So total terms are L into m, which is equal to n. Okay, so suppose if I put m is equal to 0 in this series and I start L from 0 to L minus 1. Okay, so in this power wn, your p and q now both are zeros. Okay, so p and q both are zeros. This w to the power, this will become 0. So 0 multiplied with this, it will become 0. So w to the power 0, it will become 1. This factor will always become 1. Okay, it means what you will get simply, if I keep fixed m to 0 and I vary L, I will get first x of 0 0, then x of, now m is 0, I will become 1 1 0, x of 2 0, and so on. I will get first L elements when I keep fixed m is equal to 0. The next, again when m is 1, I will again vary from 0 to L minus 1. I will get x of 1 comma 0, then x of 1 comma 1, x of 1 comma 2, again next L elements for m is equal to 1, similarly so on. Okay, and you will see that x00, x10, x20, they are nothing but they are mapped. The input data is mapped basically to these values. So it is again simply the sum of all the inputs. Okay, so x00 will be same as your x0. Similarly, you can verify that your x of 0 1, this output will be same what you get from this. Okay, so if I expand this equation, so I have xpq, which is equal to summation of m from 0 to m minus 1, l from 0 to l minus 1, x of lm, wn to the power, it was mp plus q into ml plus l. Okay, and if I expand this factor wn, you will get 4 terms. One will be, this will become ml into mp small. Okay, it will become n to the power m l then mp, ml into mp, one factor. The second will become, if you multiply this with this, you will get mpl wn to the power q ml into wn to the power ql. Okay, now this ml, it is nothing but equal to n. Okay, this factor I can write as wn to the power n into mp, and if you see, this will become 1. Okay, because wn is e raised to the power minus j 2 pi by n. If I raise it to the power n mp, so n mp, so n get cancelled, you will get e raised to the power minus j 2 pi mp, and since m and p both are integers, so e raised to the power minus j 2 pi mp, it will become simply 1. It is cos minus sine, so cos will become 1, sine will become 0. Okay, so this factor will become 1 in the multiplication. Similarly, I can write this factor as w n by m to the power pl. Okay, I have used this property here that I can write wn to the power k. I can write a wn by k, isn't it? It means I can write wn square as wn by 2. Okay, and this is very simple. If it is wn to the power k, if you see the left hand side of this, wn is what? E raised to the power minus j 2 pi by n to the power k. And if you see the right hand side, wn by k, it is raised to the power minus j 2 pi by n. Now n is basically n by k, so k will go here. So they are same. Okay, so this m I can bring here, n by m, and pl will remain here. Similarly, in this factor, it will become wn by capital L. You will get qm here into wn to the power ql. Now this n by m can be written as L. So it can be written wl to the power pl into wn by L can be written as m to the power qm into wn to the power ql. Okay, so this factor can be decomposed as a product of 3 terms like this. Okay, so I can rewrite this equation as, I can rewrite it as xp comma q is equal to, and by changing some order of summation L0 to L minus 1, summation of m from 0 to m minus 1, it was x of lm. Then we have 3 terms here now left. One is wn to the power lq, wm to the power mq, and wl to the power lp. So we can do some rearrangement here, and you can write this equation as L from 0 to L minus 1, wn to the power lq, then m from 0 to m minus 1, x lm, wm to the power mq, then finally multiplied with WL to the power LP. This is the same equation, we have just rearranged it. They both are same. Okay. Now if you interpret this equation, you will get your Fft algorithm. Okay. See, for each value of L is equal to 0 to L minus 1, if you vary M from 0 to M minus 1, if you look to this equation, this part only, this is nothing but the endpoint Dft. Okay. And if you vary L from 0 to L minus 1, if you first suppose fix L is equal to 0 here, and then I vary M from 0 to M minus 1, I will get the first row. Then you take L is equal to 1, again you vary M from 0 to M minus 1, you will get the second row. Okay. So this factor is basically nothing but the endpoint Dft of each row. Okay. So this is the first step that we have to do. You have to compute the endpoint Dft of each row. Okay. And that suppose I write F Lq, which is equal to M from 0 to M minus 1 x of Lm Wm to the power Mq. Okay, where Q is between 0 to M minus 1, so for each row, that is L is equal to 0 to L minus 1. So first you compute the endpoint Dft of each row. After computing this endpoint Dft, you multiply this matrix with a phase factor Wm to the power Lq. Okay. So second, we multiply this factor FLQ, which we have already obtained, which is the endpoint Dft of each row. If you multiply this with Wn to the power Lq, this factor, I will get a new array which I suppose write as GLQ. Okay, where L is between now, L is varying from L to L minus 1 and Q is varying from 0 to M minus 1. And then finally, when you now combine these 2 points, then finally add the output. At the outer part, we have the endpoint Dft of each column. Okay, so this is the last step. So then you compute endpoint Dft of each column. You will get XPQ, which is the final Dft. So you have 3 steps. Okay, so you first divided n into 2 factors L and M. We have stored the data in a 2-dimensional array using the column wise mapping input data. Okay, then to find the Dft, we have to compute the endpoint Dft of each row. Then you have to multiply each element of the resultant matrix with a phase factor Wn to the power Lq, and finally you have to compute the endpoint Dft of each column. You will get the final Dft, and the output Dft will be stored in row wise. Okay, this is what is the divide and rule approach. So as a simple example, to state it, suppose if I take n is equal to 15.Dft. Okay, so what we have done, we have first decomposed n as in the form of 2 factors L and M. So L is 3, M is 5. You can also take 5 into 3. L will become 5, M will become 3. So then we have a 3 cross 5 matrix. Okay, and we have stored the data column wise. It means x0 will be here, then x1, then x2, then x3, x4, 5, 6, 7, 8, 9, 10, 11, x12, x13 and x14. Okay, so this is a column wise mapping for the input. This is first step. Then what we have to do, what we have just discussed, after dividing n into two factors l and m, you have to first compute the endpoint Dft of each row. Now in this case is 5. It means I have to compute the 5-point Dft of the first row, then 5-point Dft of second row, then 5-point Dft of third row. So if you compute the 5-point Dft of these matrices, you will get a new array, new matrix. Again of order 3 cross 5. Now this row, first row, will be the 5-point Dft of this. The second row, the elements of this, they will be the 5-point Dft of this row. Third row will be the 5-point Dft of this. So you have to compute the 5-point Dft of all three rows and you have to store it here. After this, we have multiplied each element of this matrix with a phase factor. That was WL to the power LQ. So you again have a 3 cross 5 matrix. Okay, so this matrix will be mapped here, this element multiplied with WN to the power LQ. So each element of this matrix will be multiplied with this phase factor. Okay, so L and Q, you can see what is the L and Q for each point. And then after computing this, finally you have to find the 3-point Dft of each column. L point Dft, it means you have to find 5 3-point Dfts. So you find the 3-point Dft of first column, then second column, and so on, and you store the data again in 3 cross 5 matrix. So the 3-point Dft of this, that will be stored here. Then 3-point Dft of next column, that will be stored here, and so on. So finally this matrix will give you the Dft of xn, and your Dft will be stored in the row wise format. Okay, it means you will get x0 here, this will be your x1, x2, x3, x4, then x5, 6, x7, 8 and 9, 10, 11, 12, 13 and 14. This will be your final answer. Okay, this is what is Fft algorithm, divide and rule. Okay, so you have a 15-point Dft, you decompose 15 into two factors 3 and 5, you store the data in a 3 cross 5 matrix in the column wise format. You find the 5-point Dft of each row, you store them in a new matrix, then you multiply each element of this matrix with a phase factor, and then finally you compute the 3-point Dft of each column. The resultant matrix will be the Dft and the data will be stored in the row wise format. Okay, now we will see how it is efficient than the direct computation of Dft. In the direct computation, we have seen that to compute the endpoint Dft, you need n square multiplications and n minus 1 into n additions. Okay, now using this approach, it seems to be more complex, but if you compute its computational complexity, how many additions will be required? So you have to first compute the m-point Dft of each row. Now in computing the m-point Dft, how many multiplications are required? M square. Okay, because to compute the endpoint Dft, you need n square multiplications. To compute the endpoint Dft, you need m square multiplications. And how many rows are there? L rows. So total multiplications are L into m square. Okay, in the first part. when you compute the endpoint Dft of each row. So compute endpoint Dft of one row, you need m square multiplications. Total L rows you have, so Lm square is the complex multiplication, plus in the next part you multiply each element with a phase factor. It means next you need again Lm multiplications or n multiplications. And in the last case you have to compute L point Dft of each column. So you have m columns. When you compute the L point Dft of one column, you need L square multiplications. So total m columns you have into m. Okay, so you will get it as Lm into m plus L plus 1. This is the number of complex multiplications that will be required when you compute the endpoint Dft. And similarly, you can find how many additions will be required. It will become n into m plus L minus 2. This much is the number of additions that are required. Okay, now as an example, suppose this case I just take n is equal to 15. Okay, so if you use direct computation of Dft, you need n square. You need 15 into 15 multiplications. Okay, so how many multiplications are there? It is 15 square. But if I use this approach, Fft approach, I need Lm into m plus L plus 1 multiplications, and Lm in this case is 15, so I need 15 into 5 plus 3 plus 1, so it is 9. 15 into 9. Here it is 15 into 15. So your number of multiplications are reduced. Okay, or suppose if I want to compute the 100 point Dft of a sequence, and 100 I decompose into two factors, 2 into 50. Okay, you can also decompose into 10 into 10, no issue. So in case of direct computation, I need n square multiplications, 10,000. But using this, if I decompose into 2 into 50, I need how much multiplications? 100, and L into m into 50 plus 2 plus 1, so it is 53. It is 5300 only. In this case it is 10,000, so it is almost half. Okay, so the speed will basically improve. Okay, that is why we say that Fft is more fast as compared to the direct computation of Dft. Okay, so you break a endpoint Dft into smaller Dfts, and then we compute first the smaller Dfts, and then we combine them together to form a endpoint Dft. Okay, so next we will see that this is general approach. Any Dft can be computed using this. So next we will see that when n is in the powers of 2 only, when n can be expressed as 2 raised to power r, that is it can be 2, 4, 8, 16, 32 and so on, we have a still more efficient algorithm to compute the Dft, which becomes very symmetrical, that is called as Radix 2 Fft algorithm. Okay, so that we will discuss in the next class.